So what we do today, that is of your gradient divergence curve and the integrations that we can solve with the help of this operator. So this chapter actually introduce the vector field, that means the functions which is defined from your R2, R to the power 2 or R3 or R to the power n, and the main operations of your vector differential calculus other than of your gradient, because that portion of your gradient we have already studied in case of your function of several variable. So other than gradient, that is your divergence and curl. And finally, if the time permit, then we do some problem on your physical application, that is in case of your integration, shifting that the line to surface and surface to volume integral. How do you do that with this operator? Now for this gradient, what it represents, that through this gradient, as you know, that we going to find out how a scalar valued function would vary as we moved off in the arbitrary direction. This gradient also gives us the tending towards the point in which direction the greatest change of the field. As you know that if you consider any scalar valued function f of x y z equals to c, and if you take the total differentiation of that f, then that depends on your grad f with dr. Now in any direction, that means not parallel to your x-axis or not parallel to your y-axis, if you are going to compute, rather than these two, if you compute any direction, then we can find out that the change of f with in that direction will involve with your the gradient of that function, and that multiplied with your the unit tangent vector.
Sir,
Yes.
slide not visible, sir.
No, I'm not showing you the slides because I think these things has been covered, and just solve the problems before this. Just going to introduce this thing. So that directional derivative involves on your gradient of a function and the direction in which you are taking. So the direction will be given to be the normal to the surface. So therefore, if you are taking any function which is your f of x y z equals to some constant, then what we get that the change along any direction, we are getting that df ds. If we consider that s is the direction, then df ds comes to 0, and that df ds, we know that if you are going to represent them in terms of your gradient and the vector valued function, we are getting that grad f dot dr ds. Dr is the tangent vector. Ds represents the tangent vector. We need to find out the unit tangent vector. We can be getting. So that product is equal to 0. So therefore, we can get that the direction of your gradient is actually the normal to the surface, because dr ds represents you the tangent, and their dot product is equal to 0. So that must be your normal to that surface. So with this, giving you some of the problems that you can evaluate very easily. So therefore, we can find out the directional derivative with the help of the gradient, as well as we can find out the gradient at some particular point. Yes.
Are you sharing something?
No. I'm not sharing. Now I am going to share you the problems that you could solve.
But sir, your slides are visible. Yeah, means some of them are not able to see your slide. Means what you are sharing, but some of them are able to see.
No. Still now I have not shared anything. I'm just showing this slide. Now I am going to write down the
It
problems.
is not
Okay.
visible for someone.
Still, it is not visible.
No, sir, for my
No,
case,
sir,
it
it is
is.
not.
Yes,
It
sir.
is
Some are not
actually
able to see the slide only.
Not visible, sir.
Yes, sir.
Not visible, sir. Okay. I'm sharing again then.
Yes, sir.
Is it now visible? No.
Now
Yes.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So for each of the following cases, we find out the directional derivative and gradient of the scalar valued function at some particular point, and the directional derivative at that point also, but in some given vector. I think these two things you could be find it out. So for each vector valued function, scalar valued function on gradient at some point P, and the directional derivative at P along in the direction Vy. So that is number A. If you consider that f of xy, x square y, x y square at P equals to your -1 2 and V equals to 3 4. If we consider B under root of x square y square and z square at P equals to 0 -1 and V equals to your 1 1 C F Y Z X Y Z ZX at P equals to 263 and V equals to 1 - 1. So 1 and 1. So we need to find out for each of the cases of your directional derivative as well as the gradient. You know that directional derivative along any direction could be find out your which is denoted by what I am saying, that is your df. And if you consider
Sir,
any
can you
direction,
please show the previous slide? Can you show C?
okay.
So what have you written for number part C? P equal to?
P equals to 2 6 - 3.
Sir, here V is a vector or a point?
V is a vector.
Okay, sir.
2 6 3. V is a vector along which you need to be find out the directional derivative. Okay, so for that V will not always to be your unit vector, but we need to be shifted into the unit vector. Okay. So what you need to compute is that df, if you consider that any direction is denoted by your ds, so that df ds is equal to your grad f multiplied with your drds. This drds is considered to be your unit vector or unit tangent vector, rather than this represents unit vector. So the vector it is given along which we need to find out the directional derivative. So that vector is given, we need to make it transform into the unit, and the gradient of that function we could be compute, and this is called the directional derivative of that function at some point P. So we can give it to that. P, gradient is also at P.
Sir, please show previous slide once.
Yes. So all these cases, you need to find out the partial derivative of that function. As you know that the gradient of a function is ultimately the I into del x, j into del y, and k into del z operating on that function f xy or f of xyz. And then you have that the vector. So we need to find out the unit vector, and then we multiply it, that taking the dot product between them will give you ultimately the directional derivative. And at the point, whenever we have that the point is given, at that point we just replace that x, y, z by the given values of that. So I'm not computing this one. You want to solve this
Yes, sir.
three.
Minus 12 by 5, sir. A part,
You
sir.
Yes, sir. Minus 12 by 5.
okay?
Yes, sir. 1 by root 15, sir. Second, sir. B part.
So that is minus 12 by 5. This is
1 by root 15.
1 by root 15. Very good. You are so fast. Okay. So now we come to the next, what is called the divergence of a vector field. So that divergence of a vector field is gives you that
Sir, C 12 by 3, sir.
how much?
12 by root 3, sir.
12 y
Yes, sir. Divided by
by
root 3. By nahi, sir.
acha, 12 by root 3.
Yes, sir.
That is what? That is your directional derivative, or
Directional derivative, sir.
all these are the directional derivative. We also find out the gradient, so that you have already computed. That's why we are getting this one. Okay. Very good. Into the divergence, what it represents, the divergence represents that the rate of expansion or per unit volume, per unit surface area under the flow of fluid or the gas, and that we can also be compute if you just consider maybe the geometrical interpretation for divergence is given. Hello.
Sir. Yes, sir.
Geometrically it is given. Okay, so what we have, we know that it gives you the expansion per unit volume and or the contraction per unit volume. So if you're getting that the divergence of any vector valued function, if it comes to be your negative, then we can say it is actually, instead of your expansion, it is compressing. So then it means that the vector field the fluid passes through is your compressible. If you are getting the similar thing, suppose you have divergence of f is greater than 0, then we can say it will be the flow of lines of that vector field will be away from the origin. Okay, that is outside from that origin or from the source, where from the source force of line or flow of lines is originated. So that time we can say it is your positive. For example, if you consider that f is your simply xi plus yj, and if you are going to compute that is the divergence dot f, which will give you divergence is actually I into del x, so plus j del y, and f bar, so f bar is xi yj. If you take that differentiation, it comes to be your 2, which is greater than 0. So if it is greater than 0, we can say that the flow of lines directed away from the origin or the source where from it is originated. If we consider that f is equal to your minus xi, the same thing, f equals to minus.
Sir, can you please show the previous page? Yes, sir. Done.
Minus xi minus yj. Then you can find out the divergence of f by the same operator. It comes to be your -2, and that is negative. Because of that is your negative, that means the flow of lines are going to shrink to the source, or going to shrink to the origin. Okay, so but if you are getting that the divergence is your 0, then we can say that the fluid or the gas is your incompressible. Sometimes it is called your solenoidal. So that means if you are getting that f is equal to suppose minus yi plus xj, then if you take the divergence of f, it comes to be your 0. So that time
Zero, yes.
that time f is said to be your
Solenoid.
solenoidal or incompressible.
Yes.
If divergence comes in terms of x and y, then
What's that? Once more.
if x is x minus x by I cap plus x by j cap.
X I y I cap and x I x j
-1.
cap.
-1 divergent.
And -1.
Minus x by I cap means if we find divergence and it comes in terms of y and x, then what we will do? Suppose f equals to minus x y I cap
X y
I cap
I cap.
plus y x j cap.
So x y j cap. Then you need to be find out at that particular point what you are getting to be. Okay, whether you are getting to be that because in this case we are getting it is to be real, I mean linear, so we can say by just doing that divergence. But in that case we are getting in terms of your function. So for that functions,
Yes,
what it has at that
X
particular
minus
point.
okay.
So for this, the simple problem, the divergence of f j. One more type of problem is coming, that is your to find out the potential, scalar potential, that is a vector field. Vector field in the plane is supposed to be your v equals to xi. And then you can say by seeing that what is the sign of this your divergence. By seeing that the sign of the divergence, we can say whether what kind of the fluid is, whether it is expanding or it is not expanding. That we can say, because that the function v equals to xi again. So conclude about vector field with respect, with the help of sign of divergence. Next, the operator comes, that is called your curve. Now, this divergence and the gradient of a vector valued function can be.
Operator मतलब operator cross f.
Yes, that is called of f, that is operator, del operator cross the vector field. Now, in case of your divergence or the what is called the gradient, we could be compute for any dimensional vector, that could be 4 or 5. But in case of your current, we could be compute only for 3-dimensional vector, because
Sir, उसमें divergence calculate करना है first वाले में.
हाँ, just simple the divergence of that.
3xy 3xy.
3xy, okay.
Yes, sir.
3xy, right. This one is gives you 2xy and this is a 1xy. Okay, so that is called the curl. So let's define that curl as, which we take to be the your operator this cross your f, which is defined to be I j k del x del y del z, and that is your supposed to be the first component. Ith component is f1, jth component is f2, and kth component is your f3. Then we need to compute such determinant that will give you the curl of vector value function. We are getting sometimes that the determinant comes to 0, that is your curl of a vector valued function is equal to 0. That time it is said to be your irrotation, because if we go to the geometrical interpretation, we can get that it gives you the rotation about an axis. So if you're getting that the rotational value is comes to 0, so we can say that the vector field f is your irrotational. That time f is said to be irrotational. So I'm not able to say anything. The problems are verify the vector field. Equals to divide. Yes, if you have that your in case of your 3-dimensional 2-dimensional vector also, then we can get some value 0 with the coefficient of your k. So that means you can put that f3 to be 0, and then you can evaluate the determinant also. So verify that vector field is irrotational or not. Is irrotational. Of course, for xy not equals to 0.
One
Yes.
previous slide, sir.
Previous slide.
Sir, how
Yes,
to
sir.
solve this problem too
Which one?
in the current field?
Uh, uh,
A
uh,
vector field V equals to X.
oh, v equals to xi. It's v should be denoted by your velocity vector. Okay, so that is your vector value function, vector field. Now that points to the right. If you are getting that v of v equals to xi, so you can see that if we consider that the x is positive, then it gives you a vector field which is both the cases, that is for your x greater than 0 and x less than 0. These are the two possible fields. Now the length of v, this length of v will be shorter when x will be very closer to the origin, and it will be more larger when we increase the value of your x. So that means it is your expanding. For increasing of your x, that v will be expanding. So therefore, since it is expanding, so that therefore we must claim that divergence of v must be greater than 0, as we know that the expansion always indicates that the divergence is greater than 0. And that also we get you herein if you find out that the divergence of v, which comes to be your 1, and that is greater than 0.
Yes, sir. Once.
Okay. So you have to conclude with us small and simple examples. You try to conclude so that for any other problem we could come to know that what is going on therein. That is helpful. Okay, next is this one is irrotational or not. You can find out
Yes,
the
sir.
curl. It is irrotational.
Yes, sir.
This is that means your curl of f is equal to 0.
A cap into X.
Going to find curl of f equals to xy I plus x j plus k. So is this is another type. Find the scalar function. Scalar function f for a equals to y square I.
Cos X minus S K cap, sir.
That is simple. Just you need to be evaluate that determinant.
Yes, sir.
Then yes, very good. Z square k. Also so that A is irrotation. So for showing that A is your irrotational, we must get that curl of f is equal to 0. Since A is irrotational, as you know that curl of f is equal to 0 or A equals to 0, that gives you A is irrotational. And for this irrotational, if such thing will happen for any vector field, if you are getting that the curl of that vector field is comes to 0, we can say that vector field is also conservative vector. Conservative vector field. And for that conservative vector field, we are getting one scalar function. For every conservative vector field, we are getting one scalar function. One conservative for every conservative vector field, we are getting one scalar function. That is your A can be written as
2X minus 2Z, sir.
gradient of your f.
Yes, 2X minus 2Z.
Okay. Now we need to compute that of your f. Need to compute that of your f. Is this? So therefore we can say that df is equal to the gradient of f dot your dr. That much is it.
Gradient of A, sir. Or
No, df. We have that the directional derivative from that the relation from your directional derivative and the gradient of that function, scalar valued function. You're getting df equals to gradient of f dot
okay.
dr. Now this df is your a, so that much is known. df is your a dot dr. dr is your dx dy dz, I into dx plus j into dy and k into dz. A vector is given, so now we just rearrange them and integrate. That will give you that the f function. So that is one process that we can compute the scalar valued
Sir,
function.
one thing.
No,
Sir,
the
f
tomato
is
thing, yes.
a scalar function. So how can we do
Down,
grad of
down, down. Last second.
gradient is only done on vector function too.
No, gradient is only done for scalar valued function. Gradient is an operator on your scalar valued function. Okay.
Yes, sir.
But if you consider that the same operator acting on the vector valued function, then that operator we are taking the either vector operator acting on vector valued function, then we have two types of operator. One is your divergence, another is your curl. So that is for your, one is dot product, another is your cross product. Okay, but this one is always to be your scalar valued function, because that represents, that gradient of any scalar valued function will represent a vector. That is the direction of its normal to that of the surface at that particular point we are getting.
स्केलर फंक्शन मतलब फंक्शन एक्स वाई जेड में ना सर?
हाँ, function of x y z.
हाँ तो 2x minus 2z.
Which one is your 2x minus 2z? Which
Sir,
one
can
is
you
here?
solve the last problem?
This
A
one.
equals to y square. How to convert into scalar function?
This one though.
Yes sir.
Yes, sir.
The last one. How to convert into scalar function as well?
Okay. So you have that
Yes,
d
sir.
of f equals to, you have grad of f dot dr. So grad of f, as your, the vector field is your conservative, we can get one scalar function. So grad of f is comes to be your a. So that is represented by your a dot dr. What it be then? This a is equal to y square 2xy minus z square. Y square 2xy minus z square dot I dx j dy and k dj.
Yes sir.
Now you take that dot product, you have that y square dx plus 2xy dy minus z square
dj.
dj. So now we simply integrate.
Minus 2z sir.
Yes, we just simply integrate. So on integration, that gives you f of xyz. xyz. So that comes to be now when we are integrating this term, we are considering that y as a constant. So that gives you y square x. This portion is your, again that term consists of your x and y both. So we are integrating in terms of your dy when we are getting that which one is your independent of your x. So that is, there is no term, so we will not be integrate this one. Then minus, this is independent of your x and y, so we will integrate, that gives you z cube by 3.
Sir, please again repeat that point. Why we have not integrated 2xy?
What will happen, because if you integrate the same function, that function has its contribution to this expression. Okay, so we will integrate for the first one. If you integrate, anyone should mute, is unmuted. So you have this function that is your y square dx. Now if you, whenever you are integrating with respect to your x, we consider that y and z to be your constant, and then after we are getting this function. Then for the next term for dy, which does not contain the term of your x, so those terms we will be integrate, because that term has its no contribution in this case. So that has its since it consists of your the term your x, so we will not be integrate. Again for the dz, if you're getting there is no term in no term of your y and x, then only that term we will be integrate, and that integration gives you this z square doesn't contain your x and y, so we can integrate this one with respect to z. Otherwise, if it consists of your x or y, we will not be integrate, and that gives you this function. There is another process that we can do. What will happen, that the process is comes to lengthier. What the thing is, suppose you have that the vector field, you are asking that your many of the time it's used, that is your a. So now you just compare them, so that you have I into del x del f del x plus j into del f del y plus k into del f del z del f del z is equal to your some suppose a1 into I plus a2 j plus a3k. We have these three. Now we just compare. So del f del x equals to a1, del f del y equals to a2, and del f del z equals to a3. Now for by comparing these three, we will just integrate one by one and then compare with that of your del f del y. Means suppose you have del f del x, in this case del f del x, it comes to be your, the function is y square. Function is y square. So now on integration with respect to x only, so we are getting that f of x y z, x y z is equal to y square x plus the integration constant, mute yourself, plus the integration constant which is considered to be, we have considered here that y and z are your constant. So integration constant is not exactly a constant, it comes to with the form of your y and z. So how do you compute? So that y and z can be, g of yz can be computed by taking the partial differentiation of this function with respect to y, and then we compare with a2. And on comparison, we are getting that the expression will come up with this form, and then we can get the value of your g of yz in the form of your g of z only, because y comes to again
Okay, sir.
as a constant. So that process you can evaluate, but that process is lengthier. But if you follow this one, because that scalar valued function can only be represent when you have that the vector valued function is your conservative. So that idea help us to evaluate very easily.
Okay, sir. So
Yes.
we can find first that the function is irrotational or not, and then we can go through this process.
Yes, 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 yes. One more problem to solve. The vector
Please make some noises coming.
is given by a equals to x square c square g, so that the field is irrotational, hence find corresponding scalar function or the scalar potential. Okay, so with this, so today I am going to conclude. Now, one more thing is that we have the next class. I think that will be the last class because you may have the exam then after. So, but next Friday is your Holi. Okay.
Yes, sir.
So, when will you ready to attend the class?
Sir, this Monday, मतलब after vector calculus last class means Tuesday.
अबे सर नहीं है यार।
सर नहीं है भाई।
हाँ, yeah.
In here, but not on Tuesday. You take any other day, such as your Thursday or Saturday.
Sir, not on Thursday because we have
I have Viva.
Sir,
Viva.
both days we have exams, sir, Thursday and Saturday.
And sir,
Yes,
we
sir.
want some leave also
Wait,
for the
wait,
preparation
wait.
of the examination.
When
We
you
want preparatory
when
leave
you
also.
when you're I know that you require to be the prepared relief also. I have to stop the recording. The meeting is being recorded. If you want to